screen. And I don't need to see this. All right, can you all see this?
Yes.
All right, fantastic. All right, so galaxy morphology, this is my sort of my specialty. So the appearance of galaxies, and I'm going to take you through what essentially is a bunch of these chapters in the book that I wrote. And so I'll talk about very broadly what we get started. So it's 7 lectures by me, and they're also the first time I did this, it was on the CAS website. It'll be on the OAKS website this time. Learn something, no grading, no homework. It's great. So we'll talk about visual morphology, so things what galaxies as a whole look like and how people try to mathematically describe how the light looked like in galaxies. Lecture 2 we'll talk about like little things within that broad description, so sub-galaxy scales, so all kinds of things that people named in the morphology of galaxies, the phenomena that they identified. Lecture 3 is crowd classification. I'm very excited about this because this is the kind of thing where we've asked the populace as a whole rather than a single expert. And so people have helped out and identified things. I've found really strange, rare things by saying like, oh gosh, what's that? And asked an astronomer. So it was a really great, both, citizen science, it's sometimes called, but we sort of dropped the citizen part because like you don't have to be a citizen for this. So that's called Galaxy Zoo, and I will talk about crowd classification. Another thing that I've worked on a lot is called morphometrics. We'll talk about what those are, but it's basically trying to put the thing that you saw on the postage stamp and that you visually identified sort of in numbers, and like how do we turn what I saw into numbers. Then I want to do one lecture on the low surface brightness regime because you may have heard of the Rubin Observatory. The Vera Rubin Observatory is starting operations very soon. I think it's this fall. So it's the cameras going on there. The telescope is nearly completed, and so as soon as it's done, they'll start do a few trial runs, and then this is a truly gigantic digital camera that is going to take very deep pictures of the night sky, and so we'll see the surface brightnesses. So this is the features around galaxies that are so dim. They are dimmer. The night sky is brighter than, so you need to look at something very long before you see them. So this is sort of a special area for morphology, but there's a lot to learn there. And then we'll talk about how galaxies evolve, like how does morphology change, and then also what we can see in the future. And then, of course, I'll have to mention things like AI and machine learning because the numbers of galaxies that we'll have will be so gigantic that we need help classifying them, need help identifying things. And yeah, actually, that might be a good use of machine learning or an AI. So I'll talk about that as well. So visual morphology of galaxies. I have to actually identify this mad Irish Earl who it built in Ireland the at the time largest telescope. So it's a meter in diameter. You can sort of see two little people at the bottom there. This is not a photo. This is a etch, a sketch of this area. It's been recently prepared and like completely restored. But so yeah, in Ireland, which is famous for its dark skies and absolutely clear weather. He built this on his estate. Of course, he was a British royal, or not royal, but like uh, um, an earl, I think he was. So basically, he owned a whole chunk of Ireland, and so made these sketches by human eye. And so you see on the left the first of those sketches. Um, Sorry, there's like a little box here, and okay. Can anybody see that little box here, or is that not in your viewer? Okay, I'm just going to assume no. So you see two of them, right? Okay, great. There's like on the left, you see a sketch, and then on the right, you see a Hubble picture. So M51, which is one of the most famous nearby galaxies, and now if you have a telescope of your own, you can actually see something of the kind of thing that he sketched. But you see the limitation. People had to go up to the top of that tube in the middle of the night and sketch what they saw. Um, So I said already M51. Messier made a list of nebulae. So he's kept seeing these little fuzzy things in the night sky. He was a French aristocrat. So all these aristocrats apparently had nothing else to do than just do some astronomy. But he had a list of these nebulae that sort of messed up his search for comets. He was a comet hunter. That was his, thing. But he had a list of like, yeah, if you see a little fuzzy thing, don't get excited. That's already an existing, like it doesn't move. It's not a comet. Avoid these. And he's got about slightly over 100. He's now mostly remembered for his list of stuff to avoid. And so this is when you see, when I say an M number, M81, M51, M101, those are Messier numbers. And that comes from basically the very first list of galaxies, not just galaxies, as you can see here. A lot of them are galaxies, but quite a number of them are stuff in our own Milky Way or like a globular cluster. So there's a fair number of extended structures, but he found stuff that looked fuzzy to the human eye and made a list of it like, okay, if you're looking for comets, don't go there. So as soon as we had photography, as soon as photography was invented effectively, you could get much, you could aggregate more light, right? So your eyes refresh. There's a refresh rate very much like a digital camera. Or for example, you see this in if you go to a cinema, right? It's like advertised. The frame rate per second is twice as fast as the human eye. So basically, you can't even see the two individual frames change. So you see very smooth movement because you're sampling at a longer time between longer in between times. But if you do this at night, the refresh rate means that sort of your eye resets and doesn't aggregate more light. So if you want to get more light, if you want to look deeper into the night sky, you've got to use something to record the light, and that's where photography became this big deal. So the glass universe, if you're interested in history and like how all this happens, and you like books, the glass universe is one of those books where they talk about the women that worked on these glass plates. There was basically a group of observers that went out and with donkeys out into the Andes, for example, or up in Arizona, and put their telescopes up and took photographic plate after photographic plate. And then they were sent back. They were developed and sent back to Harvard. And there was this group of Harvard computers. Their title was computer, and they would compute the brightness of the stars, and they would look for these little fuzzy things. And so, yeah, they saw the first galaxy pictures. And so with that came the first classification scheme. So as soon as you have like a bunch of new data come in as a scientist and you try to make sense of it, you go like, well, these look the same and these look the same and these look the same. So I don't know what these features mean, but I have X amount of these and Y amount of that, right? So first you do the sort of butterfly collecting, and then hopefully patterns will emerge. And this was the first pattern that was sort of recognized in all these pictures. You have ellipticals, things that basically look like a football, an American football. They're seen like this. Or you have something that looks like a disc and it looks like inclined. It has these spiral arms. And then sometimes they have a bright bar in the middle. And so you can see the bottoms like SBA, SBB, SBC. These are sort of subcategories where, yes, I see a bar in the middle, and how bright is the central blob of stars, the central thing there, and then how much is that in the compared to the disk. So that doesn't tell you what it is even. It just, you can classify the pictures as you have them come in. Edwin Hubble, native of Louisville at some point, and an observer at Lowell Observatory, sort of started classifying galaxies in these broad categories. There were others, but this is the one that we sort of ended up using a lot since. So we had ellipticals. He called those early types. This is one of those things where I go, astronomers are terrible at naming things, because every time I see early and late type, I have to go look at that picture in my mind, go like early on the left, he means ellipticals. Ellipticals is much more descriptive. Early is a sort of a value judgment. Those were early, those were late. Spirals are anything that's a disk that has that spiral structures. They're sometimes called late type galaxies. You have barred galaxies that have that bar in the middle. And then irregulars is sort of the miscellaneous bin, like I don't know what the hell's going on here. So that's in over there. But this is how we talk about the appearance of galaxies. We talk about elliptical spirals, A lot of people still talk early type, late type, although I don't thank them when I have to read their paper. And then we talk about barred galaxies and irregulars. So early on the left, late type on the right. I like the term spheroidal, which means that they're basically three-dimensional, versus disk, which is like they're a very flat disk with maybe a little bit of thickening in the center. And so those are sort of the broad, very common morphologies, the shapes of galaxies. There are some limitations. The early late terminology is not descriptive, and again, I don't thank him for that. This is for broadly the optical appearance of galaxies. Galaxies can look very different if we look at different wavelengths. So this is for what it looks like when we look at it with our eyes, or photography, which is sensitive to the same wavelengths as our eyes. And irregular is not a very descriptive term, and it is really sort of a catch-all bin. But this classification scheme since 1924 has stuck, so it's 100 years old. Yay! It's a 100-year-old classification scheme, and it still works. So we then start describing this in a little bit more detail, where we go, okay, if I have a disk on the sky, what I'm seeing is like it's about yay thick on if I go for the minor axis, and it's like this long if I'm going the major axis. So I can measure that and say, okay, it's this many arc seconds of arc. It's this many degrees, this many minutes, this many seconds, and so it's usually seconds. It's this big on the major axis, and its appearance is that big on the minor axis. Now, if this is a flat disk, I'm not seeing it face on or edge on. I'm seeing it like inclined. I'm not seeing, my perspective on it isn't, from top down or right on the edge. It's actually sort of in between. So inclination, so we have a position angle and inclination. The position angle says, with respect to north, how much is, where's the major axis? So where is the major axis? Is it due north, or is how many degrees do I need to go from north to the left towards east to measure to be on the major axis of the galaxy that I'm seeing? And inclination tells me like there's no inclination, it's 0 degrees, that's face on. I'm seeing the thing from top down. And then I've got perfectly inclined, that's 90 degrees inclination. And so those are called edge on. And so if we're talking disk galaxies, it's really important what kind of inclination we're seeing. So trying to determine the inclination is important, because maybe that tells us something about, the vertical structure of galaxies we see when it's inclined, and the radial we can study when we see it from the top down, so face on. So we measure the inclination by taking the minor axis, taking the major axis, saying, okay, there's no thickening, it's just a perfectly flat one. Then to first order the cosine of the inclination, the angle between that normal line and our line of sight. So that little eye there is looking towards from left to right to the galaxy. That inclination tells us like 0 degrees, it's perfectly face on. 90 degrees is sort of looking edge on the disk. We can measure that by taking the ratio of the minor and major axis. That's sort of a first order. There's a slightly more involved one where we do assume that there is an intrinsic thickness to this thing, and so you have that was done by Hubble, and that's here. So if we say like, okay, it's not an infinitely thin disk, it's not a compact disk that none of you know what that is. Maybe your gran has one. Record player is even worse. So it's a hubcap, or well, it's a flat disk. It's a pancake, a tortilla, but the tortillas have a certain thickness. So if the whole thing puffs up, and there is a certain axis ratio that you get if you look edge on, perfectly edge on, that's called Q, and that's the intrinsic disk thickness. So this is a slightly better way of getting the inclination when I'm observing the major axis, minor axis. So it really depends if you get a nice deep picture of it, and it really depends if you can measure that well enough. So face on and edge on disk galaxies, they sort of look like this. On the left, we have the face on. We can now see the spiral structure. We can see the star forming regions in purple. This is a Hubble picture. And so you can see the detail. You can see how many arms there are. You can see dust lanes and stuff like that happen. And if I'm looking at the edge on, I'm seeing like, yeah, all that action is happening in a very thin disk. And I see a very dark stripe there, and that dark stripe is the interstellar gas and dust, and mostly dust, that's sort of blocking the light coming from further down the disk. So if you take all the dust, it's clearly in a very thin disk, and if it's concentrated like that, it's blocking the light from the far side of the galaxy. So I can actually not see all the way through that galaxy. And so that's a first thing that they started noticing. It's like, hey, these galaxies are not perfectly transparent. There's stuff in there that sort of blocks our light, and that's what I've been working on for most of my career. But so that's the thing that they started noticing, and then we go back to this classification scheme. Because, hey, what's happening then in that case with ellipticals? Does that tell us anything like what orientation we are? E1 through E7, it's just a viewing angle. I can take that football and it does if I just rotate it a little bit, I either go from something that's perfectly round to something that's incredibly elliptical. I think of it as a US football. And so they are very hard to distinguish from each other. So if I go back to spirals here, you give me a spiral galaxy and I can sort of go like, oh yeah, that's that one, right? I'll start spitting out the numbers because they have a very characteristic pattern of spiral arms and structure and stuff. They are very unique and very, sorry, nothing can be very unique, but they are very distinguished and distinguishable. Like you can tell them apart from each other. With ellipticals, they all look like this. It's a giant yellow, smooth blob. And so it doesn't really matter where you see them, and they're really hard to tell apart. People usually tell apart, oh yeah, I can see the background galaxies, for example, like that's this one. They're very hard to tell apart, and it doesn't matter from what angle you see them. Basically, that's the classification. Like along the major axis, sort of like that's an E0, and if I see it from the side, it's an E7. But it only tells me my viewing angle. It doesn't tell me anything intrinsic like inclination. So with spiral galaxies, our Milky Way is one. Andromeda is our nearest neighbor, and so both of those are examples of spiral galaxies. We think our Milky Way looks very similar to Andromeda, maybe a little bigger, maybe a little smaller. But we are inside, of course, the Milky Way, so it's really hard to see the forest for the trees, right? We're sort of in the middle of it, sort of two-thirds of the way through the disk. So we're seeing the edge-on effect, and we can't see all the way to the other side of the Milky Way, for example. So Andromeda is actually the best place to study spiral galaxies because we're sort of looking at our subject from outside. So spirals have character. Each have a certain number of arms. You can sort of identify the blue being young stars and the yellow being older stars. And you can also see that like the whole thing looks like it moves, and it does move. So the whole thing rotates, but the spiral arms rotate at a different speed than the disk of galaxies altogether. So you should sort of think the spiral arms as a traffic jam, and the rest of the disk as like this big rotating mass of stars. And so this is called M101, and this is again a Messier object. And so you can see it has 1, 2, 3, 4, 5 spiral arms, if I count right. If you count the bottom two as 2 or 1, otherwise it would be more like 3. But you can see that they're sort of bright in certain areas and then sort of interrupted, and then there's another bright area. Clearly a lot happening, right? And you see the brown stripes, that's the dust. The blue stuff is young stars, so we know that from our own Milky Way that those are O stars. These are O and B stars. They are incredibly bright in the blue, but they don't live for very long, so typically only a few million years. So if I see very blue light coming from a galaxy, the ultraviolet light coming from a galaxy, I know that stars have just been formed, because if I'd waited a few million years longer, it wouldn't be blue anymore. So the fact that the disk is blue means that it is actively forming new stars. And you can tell that the central part is yellow. That's more like our sun. Those live for like 10 billion years, even longer. And so that's older stars, and there isn't that much blue happening, so that you don't see star formation in the center. So active stuff, lots of star formation, and then like a center that's sort of dead, that isn't doing very much forming of new stars. So this is NGC 891. So that's the one that I showed earlier, and you can see edge on. You have that dark stripe, but you can see blue in there. So that's where the star formation is happening. You need that dense clouds to make stars from. Okay, so barred spirals are sort of a special class of spirals, and this is sort of the quintessential one. Again, one of those that you can see with the backyard telescope, but of course, this is the Hubble picture, and you can see there's this elongated thing in the yellow part, and it has dust lanes going along it. So something's happened there that made the central bit elongated, and then the spiral arms sort of sweep off it. So what exactly is going on? And we think bars, for example, have something to do with funneling, being a gravitational funnel, so to speak, for gas to go to the center. And so we think those dust lanes that we see is where gas gets funneled from the outer parts to the central galaxy. So, but that seems to be a very common thing. Bar research, like we'll talk about that when I get to galaxy evolution. One of the things was like, well, galaxy bars, maybe that's just a phase, right? It's how often do you hear that? Like, oh, that's just a phase, right? So this will be galaxy evolution. Bars are just a phase. So you get those, maybe something perturbed them with a tidal effect, and they're there for a bit and then they disappear. The trouble is then we shouldn't be seeing bars far, far away. But if we look at deep pictures with Hubble, we keep seeing bars, we keep seeing bars. And we just had with James Webb, look even further, and what do we find? Still galaxies with bars. So either they form, destroy, and reform, or they're much more stable than we think. So this is an area of research that we're going to hear more from in the future. How bars live, how long they live, how stable are they? This is something that we're going to look at in detail. And then I sort of left out this one fudge in the middle, which is S0. And so that's sort of in between ellipticals and spirals. It's a spiral with no disk or an elliptical with a weak one. So that's sort of how you end up. They are things that look almost like elliptical galaxies, but they have a little bit of dust. There's some evidence for a thin layer of, like, there's a bit of a disk left. And so the idea was, well, they're either spiral galaxies that sort of died out forming new stars, and there's a little bit of disk left, or they're an elliptical that still has a bit of a disk left somehow. So if you make a new elliptical, then yeah, you're still allowed, and it gets more gas, for example, then you could make a tiny disk. So that's sort of the in-between classification. And then there's the, oh yes, and other. And other are things like our own Milky Way satellite, like they're now still called the Magellanic Clouds. I grew up calling them the Magellanic Clouds. There's now a push for calling them the Milky Cloud, because guess what? Magellan didn't discover them. It's just that he noted it in his log, and now the Western world has called them the Magellanic Clouds ever since. I like the Milky Clouds a little better. So those are irregular. They don't have a particular shape. There's no neat spiral structure. There's no clear edge on or face on. There's no clear edges either. So they're very fuzzy, flunky things. And so that's often the irregular component. So we can make that with, for example, actual new pictures. And so what I showed before was were the pictures from Hubble's time. So these were photographs, and now we do this with digital photography, so we get something like this. And it really also hammers home that, yeah, if you have a disk and you're a spiral, the disk is blue. Most of the time, the disk is blue. And so you have yellow, red and dead, they're called. So red and dead meaning no more new star formation, no fresh stars. They're massive. They're often in clusters. They're often found in groups, not always, but they seem to dominate in groups. And then we have blue and star forming, less massive disk galaxies, and they're not that much found in clusters. They're found in groups. They're found in outside all of these larger structures, but that's where we find them. And so, okay, we've done the postage stamp thing, right? We've gone around with our butterfly net and found all the galaxies and sort of arranged them in a pleasing pattern. But we haven't actually done any math on this. We've done some pattern recognition. We've seen like which kinds there are lots of and which kinds there are few of. But if we want to actually see, quantify what this looks like, we use three profiles. Starting at the center of the galaxy, how do we describe the light as it goes as we go out from the center of the galaxy in a sort of radial fashion? It can either be exponential, so an exponential drop off. It's good for disk galaxies. We get a scale length, we get a typical size of the galaxy, and a normalization, so two variables. De Vaucouleurs is good for bulges of galaxies, not as soon as we get into the disk, but just the central bit, and ellipticals as a whole. And it has an effective radius, so where half the light is in, and normalization as variables. Okay, two variables. Cirsic profile also fits everything, but it has an effective radius and how the slope works, as well as a normalization. So it's three parameters, but it fits all of them, right? So it fits disks pretty well. It fits ellipticals pretty well. So it's a good way to describe all galaxies, or a reasonable way. So de Vaucouleurs is named after the author of the reference catalog. You'll see if you do research in extragalactic astronomy, something like RC3, and you go like, what is RC3? And then it's de Vaucouleurs' first catalog of galaxies, like the first big one that got made. And so he meticulously measured the light going through in his photographic plates and then fit with logarithmic tables, basically, the light profile for each of these. We have a normalized normalization, that IE, that describes how bright the whole thing is, and then RE is sort of tells you what the size of it is. But the profile is fixed. It goes, it drops as 1/4. This is easy to fit even with computers or like logarithmic tables. So you can see the appeal if you don't have supercomputers available because they haven't been invented yet. This is how you use logarithmic tables, and you can fit this law fairly quickly to your profiles that you've been measuring. An exponential profile does something very similar, but then it's like you have a central brightness, and then e to the power minus r is how far out from the radius are you, and then h is that scale length. And so those are your two parameters. I naught and h are the two fit parameters. And so that works really well as soon as you get outside the disk. So this is why I put this little plot here at the bottom. You can see that it sort of drops off very quickly. That's the R 1/4 law. So that's the de Vaucouleurs profile. And then it sort of flattens out, and that flattens out is a good exponential profile. So people initially sort of fit one to the outskirts of a disk galaxy and one to the inner bits. And so that's where you got like, okay, there's this much light in the bulge and there's this much light in the disk, and that's a good way to model it. And I can do this basically by hand with punch cards and the very first computers. So that's how we got started. But then with Sursic, and as soon as our actual computers got better, you can fit this much easier, but you use things like a gamma function. This is before we started doing all of these things numerically. And so we can approximate that BN component, but then it has three profile parameterizations, IE to normalize the whole thing, that's the intensity in the center, RE, that's the typical scale, and 1/n, that n, that Sursic index n, tells you whether or not it's like a de Vaucouleurs law, like a disk exponential, or somewhere in between. And so it allows to do something in between. It allows things to be steeper than a de Vaucouleurs, or even flatter than an exponential if you want. So you start modeling these galaxies, right? You have the data here on the left. You make a model like this. If this looks clunky and old, it's because this is definitely this is from 1986, I think. So, think the very first computational models of what these light profiles looked like. And so you can then hopefully also figure out the ellipticity, so you can actually find out what inclination we were talking about. You notice things like, hey, if I have a bar, the ellipticity changes, and also the way it's pointing changes as I go to the disk proper. So you can start quantifying things like, hey, this thing has a bar, that one doesn't. The bar is this big, it's this much of an effect. So you can actually start putting numbers on things. And so And so you have these profile descriptions, and one of the things that they start to notice is that scale length is fundamental. Like, why do they all adhere so closely to an exponential? Why is it so clean? Right? This is over the whole galaxy. You see a bit of a spiral structure. In the leftovers, you see maybe a little bit of a ring or something else. But if you average out radially, it's an exponential, and it's very close to an exponential. So that tells us something about how the galaxy was assembled. If you have a model of how you assemble a galaxy, you need to come up with an exponential disk. If you have a model, it needs to have a bulge in the center and an exponential disk. If you don't have those two, I mean, every galaxy seems to be described this way. And so as you look in the center, however, you start to realize like you want to get to those last little bumps. And then you realize you have a bulge, you have an inner disk, you have an inner bar, a lens, an outer bar, and a galaxy disk. Now that is, you start adding components. So you start adding complexity because you start resolving out the smaller components in the center. So the whole might still be an exponential disk, but the center actually had a bunch of these different components. So that gains more components, more complexity as we go along. So you can see already here that, yeah, actually, we're now dealing with 3, 4, 5, 6 different components. All of them have 3 different parameters. Wow, that is suddenly a much larger fit to the data. So as our data gets better, as we get pictures from Hubble, as we get higher resolution, we start seeing other components and we start fitting those. But they all seem to fit disk, bulge, bar descriptions. So why do we fit that? First is photometry, just to see, because they're fuzzy structures. So galaxies sort of, there's not a clear end. They sort of, as you look deeper, it becomes a little bigger because actually fainter, there was an even fainter structure around it. You look deeper and there's a little fainter structure around it. So how do I actually integrate the whole together and see like how much light is coming off this thing? So photometry. And so integrating the whole light profile is useful. A sense of scale. So if you know the distance, you now know what the typical scale is. And it turns out that galaxies, despite looking exactly the same, span several orders of magnitude in scale. So several orders meaning about 5 in both mass and size, but they still all follow that exponential profile. It's something that's really fundamental to disk galaxies. And then the relative components, for example, might tell you something else, like how big of a bulge compared to the disk. And so you quantify that rather than doing that visually, you do that using profile fit. When disks are seen edge on, however, you're now integrating along the line of sight. So you're combining all the light along the disk. So you need a different mathematical profile for that. And that's what you see here. The surface brightness in the center is that mu naught, and then R as you go out to the edges. And H is the typical scale length then. Again, same thing if you do the Sersic profile. And then Z naught is the vertical or scale above or below the disk. So instead of saying, okay, I'm just doing a radial component, I'm now also independently identifying how thick the disk is and what that looks like. So Peter van der Kruijt did that in 1981. He is my old thesis supervisor, and so I've got a special little place in my heart for this description. And it's a good way to actually look at the vertical structure and like quantify that separately. So first problem that we sort of run into is like, well, if I look at a galaxy disk and I look at it deeper and deeper and deeper, do they keep going? And it's very difficult to say because typically, if we look at, for example, with a small telescope from the Earth, our night sky, our atmosphere isn't completely dark. Even if you go to a dark site, even if you go to Kirby, for example, or you go to a good national park, you go, oh, I'm now in a really dark site. The moon's gone. I will be able to see this now, right? Well, no, it still has a brightness to it. So longer and longer integrations, something more interesting shows up. The disks don't completely keep going, but that's not everywhere. So some disks seem to be smooth. There's no break, type 1. Type 2, there's a break downwards. It actually becomes dimmer as you go further out. Type 3 is actually no, it doesn't drop off as you expected. It's actually a little brighter. So unfortunately, and especially astronomers, when confronted with a new phenomenon, will classify things into 1, 2, 3 instead of something more memorable. So I can never remember if it's what a type 1, type 2, and a type 3 is. Astronomers are bad at naming things because they found this and just named it something, right? This is still the butterfly effect the butterfly effect, like found a new butterfly, I'm calling it a type 2 butterfly. It's not helpful. So galaxies come in broad categories of disks, spheroids, and irregular shape. Hubble type describes both the bulge in the disk and the viewing angle for both spheroidal elliptical galaxies. The three radial profiles describe how the light is distributed reasonably well. They do this, however, over incredible scales, 5 orders of magnitude, 6 orders of magnitude. An exponential for disk galaxies, divocalar for spheroids, and Cersig can do both. The vertical profile is sort of like secans hyperbolicus. I'm not sure if any of you have to do that much math anymore, but it's a good description for the profile vertically. And disk profile breaks. They change gradient in many cases. Not all of them. So clearly something is up. Something tells us about the formation of galaxies. So the shape and morphology of galaxies tells us a lot what our models of galaxy construction. If we want to construct a galaxy in our simulation, we put a whole bunch of physics in, we should end up with something that has an exponential disk, for example. And some of the time that should break. And if we look at it edge on, it should have that description of secans hyperbolicus z over z naught, right? If you have something like that, great, that fits. But if not, then your model's kind of wrong. So it has to look not just look the same, it has to find the same profiles. Okay, so this is sort of what I had in mind for these sort of short lectures on a particular topic. You are exposed to some of these terms for the first time. You don't have to do any homework, yay! But that you can at least see what we talk about in astronomy. Okay, so any questions on what I've talked about today?
I am not sure yet.
Okay, that's fine.
Yeah, I'm at that point as well.
That's
a lot of
cool.
information.
I just sort of did a brain dump on you all. And so, but this is the kind of terminology that I wanted to expose everybody to. And it's the kind of thing like I took a class like literally called Galaxies, and this is what we talked about. And I realized that if I hadn't had that class, a lot of the stuff that I did in grad school wouldn't have not made sense until I've read up a bit. So that's what I'm trying to do with these classes. I'm going to stop the recording. If I figure out how, yes. So